What do wavelets look like? All Fourier basis functions look alike. A half frequency sine wave looks like a compressed low frequency sine wave. A cos wave is a sine wave translated by 90 degrees or pi by 2 radians. It takes a large number of Fourier components to represent discontinuity or sharp corners. That means to represent a square function by using Fourier series representation without any error, we need infinite number of basis functions. In contrast, there are many different wavelets and somehow sharp corners themselves. That means wavelet itself having sharp corner means original function to be approximated by wavelet takes less number of coefficients. Some of the examples for scaling functions. These are defined ones only. We can't describe without any mathematical procedure. Just for a glance we are keeping here. Some of the examples are scaling functions. Then the goal of the most expansion of a function or a signal is to have coefficients of the expansion. AJK gives more useful information about the signal than directly obviously from the signal itself. That means generally we will transform time domain data to the frequency domain means to extract some or more details of information. In a similar way, just having only time response will not give you just like a statistical properties like, so that coefficients will give some more details. A second goal is to have most of the coefficients to be 0 or very small. That means with less number of coefficients we should be in a position to represent the original signal. This is called as a sparse representation and is extremely important in applications. Example, statistical estimation and data compression, detection, nonlinear noise reduction and fast algorithms. Although this expansion is called a discrete wavelet transform, it probably should be called a wavelet series, since it is a series expansion which maps a function of a continuous variable into a sequence of coefficients, much the same way the Fourier series does, but it takes more number of coefficients. Already we discussed that J and K parameters. Wavelet series expansion in terms of two indices, the time translation K and the scaling index J. That means as you change the K value, the mother wavelet going to be translated on a time axis. When you change the J index, the mother wavelet going to be scaled in a Y axis. That means frequency axis. For the Fourier series, there are only two possible values of K, 0 and pi by 2. That means original sine wave going to be translated by pi by 2 will give you cos function. Those are the basis functions for the Fourier series, which give the sine terms and cosine terms. This value J gives the frequency harmonics. J will give you frequency harmonics. In other words, Fourier series is also a two-dimensional expansion, but if you are going to represent that Fourier series by using exponential form instead of trigonometric form. The DWT is a signal is somewhat difficult to illustrate because it is a function of two variables or indices, but we will show that DWT as a simple pulse, for example, to illustrate the localization of the transform. One example, just now we saw that some of the wavelet functions will have sharp variations. For that example, we are going to consider here hard scaling functions and wavelets. So this is the general expression. Instead of having only wavelet function, we are going to add the scaling function also to get more resolution. The simplest possible orthogonal wavelet system, here we are going to represent along with the scaling function and wavelet function. Then the scaling function of a Haar wavelet going to be shown like a simple pulse. Then wavelet function going to be shown by a square wave. By this way, if you have a wavelet itself having sharp variations, then any function having sharp variations can be represented by a few coefficients. So this is the pulse. Here just whatever we saw, djk coefficients will represent the wavelet coefficient, ck coefficients will represent the scaling coefficients. This simple pulse is going to be represented by a scaling and wavelet coefficients. Totally, with the 5 coefficients are sufficient to represent the wavelet uh, usage of a pulse representation. So that these sharp variations are also represented by a few coefficients only. That is the advantage with the wavelet trends. When you move to the Fourier series, the same type of sharp variations to be represented by sine and cos orthogonal functions will take infinite number of functions. With this, we will wind up the what wavelet looks like.